Before we dive into our problem sets today, I want to take some time to review the guiding principles behind determining oxidation numbers. So if you look in your packet, number one, the sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge of the molecule or ion. So for example, let's say we had sulfuric acid. Sulfuric acid is simply H2SO4, right? And the way that you would just calculate the overall oxidation of the entire molecule is to figure out the individual elements, the oxidation numbers of the individual elements. So you'd have 2 times the oxidation number of the hydrogens, right? Plus the, since there's only one sulfur, you'd have the oxidation number of sulfur plus the 4 times the oxidation number of the oxygens. And you just add them up and, like I said, sum them, and that is going to be your total. And in this case, it should equal out where they all kind of cancel one another, because this is not a charged molecule, this sulfuric acid. It's neutral. So that's number one, or the number one kind of rule. Number two, the oxidation number of the atoms in a pure element is 0. So what does that mean? Well, just think about like your diatomic gases or your diatomic molecules. Hydrogen, what's its oxidation number? Since there are 2 of them, it's just 0. Here's a little bit more complex molecule, a tetraphosphorus molecule. Again, its oxidation number would be 0. All right, number 3. Some elements have the same oxidation numbers in all of their compounds. So if you look at the periodic table, all of your group 1 elements, your lithium, your sodium, your potassium, rubidium, cesium, and francium, they're all going to have an oxidation number of +1. The same thing goes for your alkaline earth metals, your group 2 elements. You can see all of those are going to have a +2 charge. Now, if we kind of shift our focus over to the halogens, only fluorine has one principal oxidation number, and that would be -1. The others are found in various oxidation states. Okay, guideline number 4. Hydrogen usually has an oxidation number of +1 in its compounds. However, in compounds where all the elements are metals, its oxidation would be -1. So for example, let's say it was bonded to, let's pick calcium from the alkaline earth metals. Calcium has what type of charge on it? It has a +2. So we know that it's going to require us to provide 2 hydrogens, because each of these individual hydrogens have a charge. Oops, I should have wrote +2. So each of these individual hydrogens is going to be -1 in this context. Again, whenever it's bonded to a metal, that's when hydrogen has a negative oxidation number. Okay? Number 5, oxygen usually has an oxidation number of -2 in its compounds. However, when we're talking about peroxides, it's an entirely different story. The charge or the oxidation number on the oxygen becomes -1. So, for example, H2O2, right, this compound, hydrogen peroxide, the 2 hydrogens have an overall +2 charge, so each of these oxygens would have to have a -1 charge, so together they have a total of -2, and the molecule is neutralized. And lastly, number 6, the most electronegative element in a compound takes its lowest oxidation number, which is its group number minus the number 8. So for example, this phosphorus, let's say phosphorus, I'll give us some room. Phosphorus trichloride, for example, and which is the most electronegative element? Well, it's obviously the chlorine, right? So the way that we would calculate the individual chlorines is the group number, which is, it's in group 7, as you can see, minus the number 8. So that lets us calculate the actual oxidation number of this constituent in this molecule. So each chlorine would be worth -1, and that means that this phosphorus has to have a charge of +3, so it's neutralized. Okay, so these are the guidelines that I wanted to review with you. Let's go ahead and get our hands dirty and do some problems. Write the ionic compound formulas for A, B, and C. Okay, letter A, we have magnesium sulfate. Now magnesium, it's a group 2 element, so we know that it's going to have a positive 2 charge. Now what about this sulfate? If you'll recall, sulfate is a polyatomic ion, and so it's a sulfur bonded to a certain number of oxygens. Now do you remember that shorthand that you experienced in the lecture unit? Remember, if it's P through Z, the element to the left has to be bonded to a total of how many oxygens in order to get the ATE suffix? And the answer is 4. There it is. Okay, now what about the charge? Yeah, you could just memorize these, which you should totally do. On some of them you can kind of calculate. You could say, okay, we'll have 4 oxygens. Each oxygen has an oxidation number of -2, so that's -8. Sulfur's in group 6, so we just say, okay, +6 plus -8 equals an overall charge of -2. So the oxidation numbers are equivalent to one another, so our overall compound is just magnesium sulfate. We don't have to add any more subscripts for this molecule. Okay, what about aluminum iodide? Aluminum is a group 3 element, so +3 oxidation number, and then the iodide, so it's just iodine, right? It is a halogen. It's going to have an overall -1 charge, so in order to neutralize these oxidation numbers, our compound has to be aluminum with the subscript, or aluminum iodide with the subscript of 3 there. All right, what about barium sulfide? Now notice, this is not sulfate or sulfite, this is sulfide. So the implication is that it's just sulfur. Sulfur is group 6, so it has an overall -2 charge. What group is barium in? That's right, +2. So again, you know, their oxidation numbers are equivalent with one another. They're going to neutralize each other. So our compound is simply barium sulfide. Name the following ionic compounds. And we have A, B, and C. So letter A, first of all, we can see that we're dealing with like 2 groupings of polyatomic ions, right? This one you should know, because it's really the only positive polyatomic ion that you need to kind of commit to memory. So this is ammonium. Ammonium, and we know it has a +1 charge, and you can see here that this is a polyatomic ion. So overall, this must have really has to have a -1 charge in order to neutralize that ammonium. Now, do you remember the permanganate ion? It's really just MnO4 with a -1 charge. This polyatomic ion is very similar. The way we would reference is we would call it per-tec-nitate, and don't forget the ATE suffix there. So that's what that overall molecule is, ammonium per-tec-nitate. Okay, letter B. We know this one. This is just magnesium. Magnesium, and then this is not a polyatomic ion, it's just an element, phosphorus, so it would have to be phosphide. We got to add the IDE suffix. Okay, what about this one? Instantly we could see, okay, here we have an element, and then here we have a polyatomic ion. So this is mercury. Mercury is a transition element, so we do have to indicate what its oxidation number is or its charge. So let's figure it out. We have nitrate. Notice we have a subscript of 2, so we have 2 nitrates. Each singular nitrate has an oxidation number of -1. So overall, this has to be a charge of -2. Here we have 2 mercuries, so each of these individual mercuries must have a +1 charge. So overall, it has a +2, and then these 2 oxidation numbers neutralize. So there it is. Now we can name it. We can call this mercury. And remember, we use Roman numerals and in parentheses. Mercury 1 nitrate. Don't forget the ATE suffix on your polyatomic ion here. Calculate the charge on the ion complex. Letter A. So we know in order to determine this, we got to really make sure we understand the element that it's bonded with. And that, in this case, since it's calcium, we know that calcium is a group 2 element. There is, that means it has a +2 oxidation number, and then there's 3 of them. So overall, this calcium group here has a positive 6 charge. So what does that mean? Well, that means that the whole complex over here has to have a negative 6 charge in order to neutralize it. However, how many of these complexes do we have? Notice the subscript. There's 2. So we got to say negative 6 divided by 2 equals negative 3. So each of the complexes has an oxidation number of negative 3. Okay, that's that one. Okay, letter B. Here we have sodium manganate. Now sodium, when you look at the table, it's a group 1 element, so it has a positive 1 charge, and there's 2 of them. So overall, this whole grouping has a positive 2, or these 2 elements, these 2 sodiums, positive 2. Now what about the manganate? There's only 1 manganate. So here, this must have a charge or an oxidation number of negative 2 in order to neutralize the 2 sodiums. And this one is done. That's exactly what it is negative 2. Letter C. Here we have sodium bonded to this complex. Same situation, it's a group 1 element, so each individual sodium has an oxidation number of positive 1. There's 2 of them, so overall positive 2 charge. And as you can see, since we don't have any parentheses that we're working with in any additional subscripts, we just have to look at the complex at face value and say, okay, well, since these sodiums have an overall positive 2 charge, in order to neutralize it, the complex must have a charge of negative 2 in order to neutralize it. Makes total sense. All right, what about this situation? Well, this time we're going to switch over or adjust our focus over to the anion. We have 2 chlorines. We know that each of the chlorines has a negative 1 charge, negative 1 times 2, so our overall charge here would be negative 2. Now notice, with this complex, there aren't any parentheses. There aren't any subscripts that we really have to make sure that we're accounting for. So overall, in order to balance out this negative 2 charge, this complex must have a positive 2 charge. Okay. Letter E. We have sodium, and then cadmium, and then this complex. So let's figure it out. Well, the sodium, we only have 1, and it's a group 1 element, so its oxidation number is positive 1. And if you look at the actual cadmium, the cadmium is going to have a positive 2 charge. Positive 2. However, there are 2 of them. So therefore, we need to sum these 2. We got 2 times 2 is 4, plus 1 is 5. So overall, this section of our molecule has a positive 5 charge. So what does that mean? We need to look at our anion complex and say, okay, number 1, are there any parentheses and are there any subscripts? And there aren't, that we have to contend with, or that tells us that there are multiple complexes. That's not the case. So this whole complex must have an oxidation number of negative 5. Okay, letter F. Well, focus on the polyatomic ion. It's sulfate. We easily know what the charge is on that. Overall, it's a negative 2 charge. So what does that mean? It means that this complex better have an overall oxidation number of positive 2. However, there are parentheses involved with subscript. So we have to account for that. So 2 divided by 2 means that each of the complexes is going, or each complex, has a positive 1 charge. All right, letter G. We have magnesium as our cation. It's in group 2, so therefore it's going to have a positive 2 oxidation number, or each magnesium. There are 3 of them, so overall we have positive 6. So that means that our complex has to have an overall oxidation number of negative 6. However, there are parentheses with a subscript letting us know that there are multiples. So we're going to divide negative 6 divided by 2. That means that each complex has to have a, not positive, it's a negative 3 oxidation number. Okay, letter H. We have 4 hydrogens. We know that each hydrogen has a positive 1 charge. There's 4 of them, so our overall oxidation number would be positive 4. Now look at this complex. I know it looks a little bit like a beast with the brackets and the parentheses and so on and so on. Don't worry about it. Take a breath, exhale, you're good. Overall, you can see that we don't have any subscripts here, so we can say that this is 1 chunky complex. And we know that whatever its oxidation number is, it has to be a value that will neutralize all of these hydrogens. So simply, it's just going to be -4. And that's it. That's our answer. But let's go ahead, just for fun, and dive a little bit deeper into the complex and figure out the individual oxidation numbers. Cyanide is one of our polyatomic ions that we just need to know. Each cyanide has a -1 charge, and there are 6 of them, right? So if you think about just this value here, this would be -6. Well, overall, our oxidation number is -4. So what's the charge on this iron? And hopefully, instantly, you're saying, ah, that is iron 2. And you would be exactly right. This is iron 2 cyanide, or the whole complex. So +2 plus -6 does equal -4, which again does neutralize the +4 charge of all the combined hydrogens. Write the chemical formulas. Okay, so letter A, cobalt-2 nitrate. Well, we're given the actual oxidation number on the cobalt. It is a transition element, or transition metal. So we got cobalt, and it has a +2 charge. Now what does nitrate look like? That's one of our polyatomic ions, NO3. However, remember what the charge is. You either can memorize it, or you can do my kind of shorthand method where you say each oxygen has an oxidation number of -2 times the 3 of them, overall -6, and just look at the group number of nitrogen and use that as a positive value. In this case, nitrogen is in group 5, so +5 plus -6 equals an overall oxidation number of -1 on the nitrate. So the problem is we need enough nitrates in order to neutralize that +2 charge on the cobalt. So our formula would require us to use parentheses. Put that nitrate in parentheses, and then we got to add the subscript of 2. Now it's neutralized. Awesome. Okay, radium nitrate. Well, radium's a group 2 element, so it has a +2 charge, and really it's basically the same idea. Radium, then our nitrate, each nitrate with a -1 charge. Again, we're going to have to employ parentheses again, NO3, and then 2 of them. All right, letter C, tin-4 nitrate. So our tin has a +4 charge to it. Each nitrate is -1. So again, we're going to use parentheses because we're going to need 4 of those nitrates in order to neutralize this +4 charge. All right, letter D, arsenic-3 nitrate. All right, so you got arsenic with its +3 charge. We got each of our nitrates with a -1. So it's the same story. We have got to use parentheses. How many of them do we need? Well, we need 3 nitrates to neutralize the +3 charge on the arsenic. All right, letter E, gold-3 nitrate. So here's our gold, +3. Here's our nitrate. Just the same idea. We'll use parentheses, and we need 3 nitrates to neutralize the gold. All right, now letter F. It wants us to go back and look at all of these cations as if they were bonded to sulfite. Now let's think for a second. What is sulfite? Well, it's kind of like sulfate. Remember what sulfate is? It's SO4. What is the charge on sulfate? Again, you can memorize it, or you can use my method in order to calculate it real quick. Each oxygen has an overall oxidation number of -2. There are 4 of them, so overall it's -8. Sulfur's in group 6, so we're going to count that as +6. Just sum the 2 values. So the overall oxidation number of sulfate is -2. But sulfate ends with the suffix ate. We're asked to use sulfite. So what do we have to do as far as our number of oxygens? And if you'll recall from the lecture, all we have to do is strip away one of those oxygens. So it becomes SO3. Now here's where maybe this tricks people up, or people just seem to forget sometimes. What is the oxidation number on the sulfite? Recall that you're not going to have to recalculate the oxidation number. You will always retain the charge of whatever the ATE form is of that polyatomic ion. right? So if sulfate is -2, that means that sulfite is going to have an overall -2 charge. So let's go back through and we'll go ahead and do our new compounds as if they're bonded with sulfite. So we have cobalt 2 sulfite. Now think about that. Cobalt just has a +2 charge. So we'll say cobalt and then our SO3. That one is done. All right, radium. Radium has a +2 charge. Sulfite has a -2 charge. It's done. RaSO3. Awesome. Next, tin 4. So we have SN. And now we're going to have to use parentheses for our sulfite because the tin has a +4 charge. We need a -4 charge in total from our sulfite or our anion within this molecule. So how many of these do we need? We just need 2 because 2 times -2 is -4. That cancels out the +4 on the tin. Next, arsenic 3. Okay, now think about this one. Arsenic has +3, and we know that the sulfite is overall -2. So what do we need here? Well, we're going to have to adjust our arsenic. We're going to need 2 of these to get an overall oxidation number or an overall charge of +6. Again, it's the lowest common multiple here. And then our sulfite, yes, we're going to have to employ parentheses. How many of these do we need? Well, remember, it's -2, so we need to have an overall -6 charge. Therefore, we need 3 of those. And that compound is neutralized at this point. All right, gold 3, exact same story. I'll just go for it. So we're going to have, since it has a +3 charge, we're going to have 2 of those to equal an overall +6. And then our sulfite, we're going to need 3 of those to yield an overall -6 charge to neutralize the gold. And that's it. That's the process. Name the compounds. Letter A. So we have aluminum and we have sulfur. So there's nothing in particular that we have to do. We can just name the metal, the non-metal, and add the suffix IDE or I. So this becomes aluminum sulfide. All right, what about letter B? Now SB, what is that? That's antimony. Antimony is a transition metal. So what does that mean as far as the naming process? We're going to have to incorporate the charge using Roman numerals. So antimony, I'm going to start with that. Antimony, and I know I'm going to have to list the charge, and right now I'm just going to leave it parentheses. What about our anion in the molecule, or excuse me, in the compound? It's sulfur. So it's not a polyatomic ion, so I can still use that suffix, the IDE suffix, sulfide. Now let's get to work, and we need to calculate the oxidation numbers or values here. Well, okay, some interesting things are going on now. Sulfur is a group 6 element. Each individual sulfur has an oxidation number of what? -2. We have 5 of them. So 5 times -2 equals -10 overall. So I'm going to write -10 over here. So that means that this antimony, we've got to neutralize that -10 charge. So we know overall this has to be a +10. Now how many antimonies do we have? We have 2 of them. So just take 10 divided by 2, and what is that? That's +5. So each antimony, it has to have a oxidation number of 5 or +5. So we say that this compound is antimony 5 sulfide. You get the process? Pretty straightforward. All right, what about the next one? Again, it's antimony. It's basically the same thing, except it's a different form of antimony. It's going to have a different oxidation number. So I'm just going to go ahead and do what I did before. I'm going to write antimony. And of course, I'll include my parentheses in sulfide. Okay, now let's get in and do the work. Again, each sulfur has an overall charge of -2, but this time we have 3 sulfurs. So our overall oxidation number or overall charge is -6. So that means that this has to be +6 in order to neutralize it. How many antimonies do we have? We have 2 of them. 6 divided by 2 is +3. So this one is antimony 3 sulfide. All right, what about letter D? We have aluminum and we have a nitrogen. Again, it's not a polyatomic ion in this particular situation, so we can just name it as a normal ionic compound. We have aluminum, and then we can just say nitride, IDE suffix. All right, what about letter E? Again, we have aluminum, but notice we have a polyatomic ion. Now, aluminum is not a transition metal, so we don't have to notate the charge. We can just say, okay, that this compound is aluminum, and then now name the polyatomic ion. It's just sulfate and ATE suffix, because why? This sulfur is bonded to 4 oxygens. All right, what about letter F? This time it's aluminum and a variation of that sulfate. We stripped away 1 oxygen, and if you'll remember, once you do that, it's no longer the ATE suffix, it is the ite, or the ITE suffix. So we'll name this aluminum, and instead of sulfate, we'll say sulfite. There it is. That's an E, by the way. So there's our difference in suffixes. All right, got the same thing going on here for letter G and letter H. We have aluminum, but we don't exactly have nitrate, right? We strip away 1 oxygen, so it has to have the ite suffix. So we'll say aluminum nitrite. And then the last one, this one's easy. It's NO3, that is indeed the nitrate polyatomic ion, and it's aluminum nitrate. That's our solution. Mercury, lead, thallium, and barium are heavy metals that are found in many toxic compounds. The most common ions are lead-2, thallium-1, and mercury-2. What are the formulas of these metals when bonded to carbonates, sulfides, nitrides, and bromides? All right, let's make a list of what we're working with. First of all, we have mercury, and it said the most common form would be mercury-2. So I'm going to make a little note here as far as the oxidation number. And then next we have lead, and the most common oxidation or version of lead would be, again, +2. We have thallium, it'd be +1. And then we have, what was it? It was barium, just Ba. And barium is a group 2 element, so +2. Okay, cool. And then what are we bonding it with? Well, carbonates. Let's kind of review our polyatomic ions here and make sure we understand their charges. So, first of all, we had carbonate. Now, what is the charge on that? Each oxygen has an oxidation number of -2. There are 3 of them, -6. Carbons are in group 4, so 4 plus -6 is an overall charge of -2. What was next? We were told sulfides. Well, what's a sulfide? I mean, sulfide is just sulfur, and that's going to be -2. What else? Nitrides. Nitrides would just be our individual nitrogens, and if you look at the group number, 5 minus 8, that's going to have an overall charge of -3. The last one was actually bromides. Bromides. So those are all going to be -1. -1. Okay, cool. All right, let's go for it. We'll do all these for each one, right across. So first we have mercury, and if it has a +2 charge, and we're bonding it with carbonate, the +2 and the -2 are going to neutralize. So it just becomes mercury 2 carbonate. All right, well, what about the sulfur or the sulfite? Again, an overall oxidation number or overall charge of -2. So again, they're going to cancel. That's pretty easy. All right, what about the nitrogen or the nitride? -3. Well, that means that we're going to have more than one, or more than one mercury, because each mercury in this context has a +2 charge. So we're going to need to have an overall +6. How do we do that? Well, the way that we do it is we have to have a subscript of 3. So we need 3 mercuries that have a +6 charge. And then what about our nitrogen? Well, each nitrogen has a -3, so we need 2 of these guys to yield a -6, where they neutralize. Okay, what about the bromine? Well, this one's easy. You got our mercury, and then we're going to need 2 bromines. So mercury, 2 bromide. There you go. That's the process, guys. So let's go for it. Lead 2. It's more or less the exact same thing. Just put in lead, take out the mercury. So here we go. Lead 2 carbonate. We got lead 2 sulfide. We have lead. Now, again, we're going to have to use the same subscript because why? We need an overall positive 6 oxidation number or overall positive 6 charge from all of our leads. And then here's our nitride. We need 2 of those. And then our bromines, we're going to need 2 of those to cancel out the positive 2 charge on the lead. Okay, thallium has a positive 1 charge. Carbonate negative 2. So clearly we need to use a subscript of 2 so we have an overall positive 2 charge on the thalliums. So that's thallium carbonate. All right, sulfide, same story. We need 2 of them. All right, what about the nitrogen? Well, this time we need a subscript of 3 to have thallium 1 nitride. And then the bromine, when the thallium is bonded to the bromine, it's just the TLBR. That's it. Okay, thallium bromide. Awesome. All right, barium has a positive 2 charge. Carbonate has a negative 2 charge. They neutralize. And so we just get barium carbonate. That's good. Sulfide, exact same situation. So we're going to say barium sulfide. Then the nitride, now we're going to have to use multiples. And what's their lowest common multiple? It would be 6. So what can we do? How many subscripts or how many bariums do we need? We need 3 bariums to yield an overall positive 6 charge. And then the nitrogen, since it's negative 3, how many of those do we need? Well, we need 2 of those nitrogens. Now this compound is indeed neutralized. All right, next, bromine. We got positive 2 on barium, negative 1 on the bromine, so we need multiple bromines. So we'll just use the subscript 2. Okay, for this next section, we want to talk about Lewis structures and the mechanics of actually producing them. So I have the individual steps that I want to cover with you right now. Of course, this is in your packet. Follow along with me. Step number 1, you're going to find the total number of valence electrons. Again, using the periodic table, looking at the group numbers and so forth. Number 2, or step number 2, if there is more than 1 atom type in the molecule, put the most metallic or least electronegative atom in the center. Now I want you to recall that electronegativity actually decreases the further we get away from fluorine on the periodic table. Step number 3, arrange the electrons so that each atom contributes 1 electron to a single bond between each atom. Step number 4, count the electrons around each atom and ask yourself, are the octets complete? And if so, your Lewis structure, you're done. Step number 5, if the octets are incomplete and more electrons remain to actually be shared, we'll start moving 1 electron per bond, per atom, to create another bond. Now, there are going to be some structures that will be open octets. For example, the boron in BF3, or there's other atoms that have 10 electrons like phosphorus in PF5, and then even some that have 12 electrons like sulfur in SF6. Okay, step number 6. We're going to repeat steps 4 and 5 until all octets are full. And the last step, number 7, redraw the dots so that electrons on any given atom are in pairs whenever possible. So we'll come back to these steps and reference them as we do all these problems because we're going to get plenty of practice. But before we do, I do want to show you just some basic or some very general bonding patterns that we always have to remember. Sometimes we can miss the forest for the trees and we get so deep into what we're doing and we make simple mistakes like putting too many bonds on carbon. So carbon, and I'll start with carbon. Carbon is always going to have 4 bonds. Really no more, no less. Now it could have lone pairs and we'll deal with those situations when we reach that point. However, remember, carbon has got to have 4 bonds of some type, okay? Hydrogens. Hydrogens can only form 1 bond. Now what about halogens? And I'm just going to use this variable X to represent all of our elements in group 7. Halogens, more often than not, only form 1 bond. However, they do have lone pairs. Since they're in group 7, right, there's 2, 4, 6, and then here's their 7th electron right there. What else? Oxygens. Oxygens generally are going to form 2 bonds. So don't forget though, they also have 2 pairs of lone electrons. And then the last one I wanted to share with you guys was nitrogen. Nitrogens generally are going to form 3 bonds and retain a lone pair of electrons as part of the overall molecule. So these general bonding patterns, if you'll commit these to memory and don't lose sight of them, you should be very successful as you move forward and draw Lewis structures. Draw Lewis structures for the following compounds. So letter A, we have methyl chloride. Okay, so methyl, we have a carbon, and we know that there's a chlorine that's involved, and then there's going to be 3 hydrogens here. So I'm just going to arrange the molecule like this. Now let's go through our process and determine the total number of electrons that we're working with. Well, first of all, the hydrogens, we have 3 of them, and each hydrogen has 1 valence electron. And then the carbon, we only have 1 of those, and it's in group 4, so we have 4 valence electrons. And then we have 1 chlorine, which is in group 7. All right? So now, 11 and 3 is 14. 14 total electrons that we have to account for within our Lewis structure. Now I'm going to go forth and just add the individual valence electrons. I know that this hydrogen has that valence electron, this one has that one, this one has that one. Okay, that takes care of the hydrogens. Now the carbon. I need 4 valence electrons around the carbon. And then the halogen, which is chlorine, I need 7. So I'm going to go ahead and put them in lone pairs here. And then the 1 individual electron pointing towards the center. And now all I have to do is really kind of connect the dots and create the bonds. And so there's a bond that forms here. Remember our bonding patterns. Carbon has to form 4 bonds. Hydrogens can only form 1. There's a bond. There's a bond. And then there's 1 bond there. Now we need to account for all of our electrons, our 14 electrons. So here we go. 2, 4, 6, 8, right? 10, 12, 14. This Lewis structure is complete. And if you want to kind of clean it up and give it a little bit more of a pristine visual appearance, you can just do it like so. Just with the individual lines, but please don't forget the lone pairs on the applicable elements. Okay, cool. What about ammonia? Ammonia is the molecular formula, or the compound looks like NH3. So we have a nitrogen, and then it's bonded to 3 hydrogens. So it doesn't really matter where you place them. I'm just choosing to do it this way, but of course you can have a hydrogen up here or whatever. It doesn't matter. But now let's go through our process and calculate our total valence electrons. Again, we have 3 hydrogens. Each one contributes 1 valence electron, plus our nitrogen, which is in group 5. So that's 5 valence electrons. So I didn't need that closed parentheses, but we need once we calculate this, we see that it's a total of 8 electrons that we're accounting for. Okay, now let's go for it. Here's our singular electron on that hydrogen, that one, and that one. And then let's do our 5 for the nitrogen. So 1, 2, 3. And then remember the bonding pattern for the nitrogen, typically it has a lone pair. So there's the 5. Okay, let's create some bonds. Here we go. There's a bond. There's a bond. There's a bond. Can't form any more bonds. Let's make sure that we do indeed have the 8 total electrons within the molecule. 2, 4, 6, 8. This one is done. All right, letter C, carbon dioxide. So you can tell just by looking at the molecular formula is that the carbon is going to be centralized. It's going to be surrounded by 2 oxygens. Now let's go through our process and determine the total number of electrons that we're accounting for. So we have 4 electrons contributed by the carbon plus 6 individual electrons from each of the 2 oxygens. So we're looking at 12 plus 4 is a total of 16. Okay, now I'm going to go through and I'm just going to put all the individual electrons on each of the elements. So there's our 4 valence electrons on the carbon, and I'm going to do the oxygens. If you'll remember the general bonding patterns for the oxygen, normally there's 2 lone pairs, so there they are. And I'm going to do the opposite on this side. There we go. All right. Now I'm going to go ahead and connect the individual atoms and create the bonds. So there's a bond, there's a bond, but right away you can see we have a problem. There's 2 electrons on the carbon that want to bond. Remember, the general bonding pattern for carbon is 4 bonds. So what can we do? Well, what we can do is we can essentially create a bond there. So a double bond. Well, what about this one and this one? Well, we could basically do the same. Now, I'm going to clean this up visually and make it look a little bit more precise. So I'm going to get rid of this. And I'm going to get rid of that one, or that electron, and I'm going to get rid of that electron. And I'm going to bring that electron that was there, I'm going to bring it right here, and I'm going to bring the electron that was down here, I'm going to bring that there so we can form this double bond that occurs. And the same idea on the other side of the molecule. Here are the 2 electrons, and I'm drawing their bond, boom, there it is, double bond. So if I was going to clean this up, it would just kind of look like this. Double bonded, and don't forget your lone pairs. And I'm putting them on opposite sides of the oxygen. And let's go ahead and make sure that we have the correct number of electrons. Again, we need 16. 2, 4, 6, 8, 10, 12, 14, 16. This Lewis structure is complete. All right, now what about the C2H2? This is acetylene. And we have 2 carbons. Remember, each carbon generally wants to create or have 4 bonds, and each hydrogen wants to have 1 bond. So I'm going to set it up like this. I'm going to have a carbon bonded to the other carbon, bonded to hydrogens on each side of the compound. Now let's go through our process. We have 2 carbons. Each carbon contributes 4 valence electrons. We have 2 hydrogens. Each of those contributes 1 valence electron. So we have 2 times 4 is 8, plus 2 is a total of 10 electrons. Oops, what am I doing? 10 electrons that we need to account for. Okay, let's do it. Let's have our individual electrons. Here's 1, 2, 3, 4. We'll do that there, 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 and there. And now for our valence electrons on our hydrogens. Okay, let's create some bonds. I'll do the hydrogens to carbons first. There's 1 bond. There's another bond. Let's do the center bond between the carbon. Now notice our carbons, they have unbonded electrons. Well, we need to create new bonds. So technically, these 2 electrons can come together and form a bond. And the same is true of these 2 singular electrons. So look at this. We have a molecule with a triple bond between the carbons, and this is exactly what acetylene looks like. I'll show you the cleaned up version of it. Boom, there it is. And that little structure is complete. Again, 10 electrons, 2, 4, 6, 8, 10. Yes, sir, it's done. Ammonium ion for letter E. Now we have an ion. We cannot lose sight of that. Remember, an ion is not going to have the same number of protons and electrons. It's either going to be positively charged or negatively charged. In this case, it's ammonium. And you'll recall, ammonium is NH4 with a positive 1 charge. So we can't lose sight of that. Now notice we have a nitrogen. And this time it's bonded to 4 hydrogens. So I'm just going to place them all around the nitrogen. All right. Let's go through our process. Nitrogen, since there's only 1 of them, it contributes 5 valence electrons, and then we have 4 hydrogens. Each one of them contributes 1 electron. So we're good so far. However, there's one critical step that we have to make sure that we follow in our overall calculation. Since this is an ion, it has one less electron. So we need to account for that. We're going to say minus 1 electron for our total. So we have 5 plus 4 is 9, minus 1 gives us a total of 8 electrons in the end that need to be accounted for. All right, now let's go ahead and just do our individual valence electrons. I'm going to add the singular electrons on all the hydrogens. And then what about the nitrogen? We remember nitrogen generally has a lone pair and then 3 ready to go electrons, ready to form a bond. Well, we lost 1 electron, so what I can do is I'm going to remove one from the lone pair, and everything should work out now. Let me form the bonds. Here we go. There's 1 bond, there's a second bond, a third, and a fourth. And I'm going to account for the electrons. I should have 8. 2, 4, 6, 8. Yes, sir. This thing is done. Now, here's one thing that you have to remember when you're drawing ions or polyatomic ions as Lewis structures. There's a very specific formatting that has to occur. We have to use brackets. And in addition to the brackets, we also have to indicate what the ionic charge is. In this case, it would be positive 1. So you place that in the upper right hand or the upper right hand corner of just outside the brackets. So a cleaned up version of this Lewis structure, you just have the nitrogen, you'd have your 4 hydrogens, and again, you must put them in brackets, and do not forget your overall charge.